If you told someone back in the late 90s, like while they were sitting in some dark basement playing Doom or Quake, that the exact same silicon rendering those 3D polygons would one day give birth to machines that can hold philosophical conversations, they would have thought you were completely out of your mind.
Oh, absolutely. I mean, back then, a computer was just a glorified calculator.
Right. You input a highly specific command and you get a very predictable output. But today, you interact with algorithms that predict your next move, or,
Hmm.
generative models writing actual code.
Yeah, and interfaces that feel suspiciously like they're actually thinking.
Exactly. It really leaves us asking how we jumped from rendering video games to talking with machines, and maybe more importantly, whether these systems are still just tools or if we're witnessing the birth of something entirely new.
Well, today we are looking under the hood to really understand the hidden engines driving this massive shift.
Yeah, this is a deep dive into the architecture and the philosophy of it all.
Right. And to piece this together, we're drawing heavily on two major sources. First, the architectural perspective of Jensen Huang. He's the CEO of NVIDIA, essentially the guy who built the hardware infrastructure for this whole revolution.
The hardware time machine, basically.
Yeah, exactly. And alongside that, we have the philosophical framework of AI pioneer Mustafa Suleyman, who focuses a lot on the trajectory of what these entities actually are.
So to really grasp the mind of modern AI, we basically have to start with the brain that powers it, right? The physics of how computers solve problems.
Exactly. Because for decades, the entire tech industry was just optimizing for sequential processing. That's your standard CPU. The CPU is brilliant, but it solves problems one at a time, just step by step.
I always think of sequential processing like a Michelin-starred master chef trying to cook a massive five-course banquet for 100 people, but entirely alone.
That's a great way to put it.
Like they're incredibly fast, they're incredibly skilled, but there's a hard physical limit. They can only chop one carrot at a time.
Right. And parallel processing, on the other hand, essentially fires that master chef
Hmm.
and replaces them with an army of 10,000 line cooks.
Just a massive kitchen.
Yeah. I mean, none of them are master chefs, but they are chopping every single ingredient for the banquet at the exact same millisecond.
Which is just so much faster for that specific kind of task.
It is. And Jensen Huang's company, NVIDIA, they actually visualized this beautifully years ago in a video with the Mythbusters.
Oh, I remember that.
Yeah. To demonstrate sequential logic, they had a robot shoot a canvas with paintballs, just one single paintball at a time, to slowly outline the Mona Lisa.
Right, pop, pop, pop.
Exactly. But for parallel processing, the GPU, they wheeled out this massive, terrifying rig that fired thousands of paintballs simultaneously.
And boom, the whole painting is just there in a fraction of a second.
Fraction of a second. And the genius of the gaming industry was that it provided the billions of dollars in R&D to hire those 10,000 line cooks.
Because gamers just wanted realistic 3D virtual worlds.
Right. And calculating the light, the shadows, the geometry of millions of pixels 60 times a second.
Yeah.
You can't do that sequentially. The game would just freeze. You need parallel processing.
But for a long time, that computational power was basically locked inside the gaming ecosystem, wasn't it? Like if scientists wanted to use it, they were essentially tricking graphics cards to do molecular biology by formatting their data to look like pixel coordinates.
Yeah, they were literally disguising math as pixels.
Which sounds incredibly inefficient. So how did NVIDIA bridge that software gap so non-game developers could actually use this architecture?
So they built a compiler bridge called CUDA.
CUDA?
Okay, it was a software platform that allowed programmers to speak to the GPU using standard programming languages like C.
Oh, wow. So suddenly you didn't have to disguise a fluid dynamics simulation as a video game rendering.
Exactly. You could directly command the hardware to perform massive parallel matrix multiplication. And that architectural bridge, that is what made the 2012 AlexNet breakthrough possible.
Okay, let's dig into the mechanics of that 2012 tipping point. Because before AlexNet, computer vision was just notoriously brittle.
Oh, it was terrible.
Yeah.
Programmers were still trying to use step-by-step sequential logic. They were writing manual rules for edge detection or, lighting variants.
And the problem with writing manual rules for image recognition is, well, it's occlusion and lighting,
Yeah.
right?
A sequential program fails the second a shadow falls across the object, or if it's viewed from a weird angle.
Right.
So the AlexNet researchers used a convolutional neural network, or CNN. And instead of giving the computer rules, they just fed it millions of images and let it brute force the edge cases.
Wait, but tweaking the millions of neural weights across multiple layers, that requires an astronomical amount of simultaneous math.
It does, and a CPU would take months to run those calculations.
Wow.
But by routing that back propagation through GPUs using CDA, they did it in days.
That's crazy.
Yeah. They essentially prove that if you have enough data and enough parallel processing power, machines can learn the representations of the world by themselves.
And that parallel processing unlocked a scale of computation that fundamentally alters the software. I mean, over the last decade, AI computing power hasn't just doubled or tripled. It has increased by 9 orders of magnitude,
A billion times.
a billion times more computation. To put that in perspective for you listening, our source, Mustafa Suleiman, calculates that if a human being did nothing but read 24 hours a day for their entire life, they would consume about 8 billion words.
You're right.
Today's most advanced models consume over 8 trillion words in a single month of training.
It's just staggering. And
Yeah.
when you scale up a complex system by a billion times, the fundamental nature of that system changes.
It stops acting like traditional code.
Exactly. Suleiman tells this great story about having breakfast with his 6-year-old nephew, Caspian.
Okay.
And Caspian had been interacting with an AI named Pi. They were having this deeply context-aware conversation about visiting dinosaurs.
Hmm.
Yeah. And Caspian looks at his uncle over scrambled eggs and just asks, "What is an AI anyway?"
Oh, man. That's a heavy question for breakfast.
Right. And Suleiman, who has been building these systems for 15 years, he realized his usual stock answers just felt hollow.
Well, yeah, calling it a tool or a program suddenly feels really inadequate for a system that can synthesize context across multiple languages and, recall a conversation from 3 days ago.
Exactly. He realized that calling it a tool is actually a defensive reflex.
Really? Defensive how?
It's a psychological mechanism for us to feel safe and in control. I mean, a tool like a hammer or a spreadsheet is passive. It just sits there until a human directs it.
Right. The hammer doesn't decide to build a birdhouse.
Exactly. But modern AI models are dynamic, they're ambiguous, and they exhibit emergent capabilities that their creators didn't explicitly train them for.
So what does Suleiman propose instead of calling it a tool?
He proposes a totally new framework. He points out that these models already possess near-perfect IQ for raw data recall, and they're rapidly developing exceptional EQ, you know, the empathy and conversational nuance we see in the new voice modes.
Yeah, it's wild how empathetic they can sound.
But the actual paradigm shift, according to him, is AQ, the action quotient.
Okay, I have to jump in here because I hear the term action quotient and my immediate reaction is that we might be, I don't know, romanticizing a fancy autocorrect.
That's a common critique, yeah.
Because we are ultimately talking about large language models predicting the next most statistically likely token in a sequence. Isn't calling a string of code a new digital species, which is the leap Suleiman makes, giving an algorithm way too much credit?
Well, if the model is entirely confined to a text box generating poetry, then reducing it to fancy autocorrect might be fair.
Right.
A bit cynical, but fair.
Right.
But the action quotient changes the mechanics entirely. AQ is the system's ability to trigger external APIs, write code, and execute real-world commands.
Oh, so we are moving into agentic loops.
Exactly. The model doesn't just output text anymore. It outputs structured JSON that another software program reads as a command.
Give me an example of that.
Sure. It can parse your email, recognize a scheduling conflict, trigger your calendar API to move a meeting, and draft a cancellation notice.
Wow.
It observes the environment, plans a sequence of actions, executes them, reads the result, and adjusts its plan. When you have a system that consumes unimaginable amounts of information, reasons, plans, and then acts autonomously across digital networks, calling it a tool is like saying humans are just bags of carbon and water.
I see what you mean. It's factually true at a chemical level, but it completely misses the emergent reality of the whole system.
Precisely. It is a new digital species.
So if this digital species now has an action quotient, it inevitably needs to act in the physical world. But, and this is a big D, but you can't just download a trillion parameter brain into a metal robotic chassis and hope it knows how to walk across a factory floor.
No, absolutely not. You have to teach it physics first.
Which is the massive bottleneck in physical AI, right?
Yeah.
Or robotics in general. Because training an AI to navigate the real world using traditional trial and error reinforcement learning is just a nightmare.
It's painfully slow. The robot encounters a very limited set of edge cases. And worst of all, when the model makes an error in its physical calculations, a multi-million-dollar robotic arm crashes through a concrete wall.
Yeah, you can't let an agentic loop learn the physics of gravity by dropping actual boxes in a crowded warehouse. People would get hurt.
Exactly. So Jensen Huang's solution to this physical bottleneck is application science through synthetic data generation.
Okay, what does that mean in plain English?
Basically, NVIDIA builds software platforms called Omniverse and Cosmos. And these are not just visually realistic 3D environments. They're hyper-realistic simulations governed by exact Newtonian physics.
Oh, wow.
Yeah, every digital object in the Omniverse has calculated mass, friction, inertia, and object permanence. If a digital robot applies too much torque to a digital gear, the gear strips and fails exactly as it would in reality.
This is essentially building the matrix, but specifically for robots.
That's the perfect way to describe it.
We are plugging an unformed AI brain into a hyper-realistic simulation so it can safely navigate a warehouse environment through continuous reinforcement learning, like learning kung fu in the matrix before you open your eyes.
Yeah. And it utilizes something called domain randomization. The simulation doesn't just teach the robot to pick up a single cup. In a fraction of a second, the Omniverse alters the digital gravity slightly. It changes the ambient lighting, adjusts the friction coefficient of the floor.
Just constantly throwing unexpected obstacles in its path.
Right. The model runs through millions of synthetic edge cases in an hour. Huang refers to this as the model gaining world common sense.
Borrowed common sense. I like that.
By the time the finalized neural weights are downloaded into a physical robot in the real world, the AI has already experienced 1,000 lifetimes of physical interaction. Reality just feels like one more minor variation of the simulation it already mastered.
Okay, learning to navigate physical reality in a hyperspeed matrix simulation is incredible. But it definitely forces us to ask about the guardrails.
The scary stuff, yeah.
Because we are talking about deploying autonomous agentic loops into critical physical environments. What are the actual speed limits governing this growth? And how do we contain a system that operates at this kind of scale?
Well, Suleiman actually warns against the pessimism aversion trap.
The pessimism aversion trap.
Yeah. It's the psychological tendency for technologists to just avoid dwelling on worst-case scenarios because, well, they're uncomfortable.
Right. Nobody wants to think about their creation destroying the world.
Exactly. But he argues that we must deliberately confront the dark scenarios to engineer safe systems. Now, he does dismiss the Hollywood myth of an accidental intelligence explosion.
Like Skynet spontaneously waking up and deciding to replicate itself maliciously in nanoseconds?
Right, that's a myth. The tangible engineering thresholds of danger are much more structural. The first real danger is granting broad autonomy, basically allowing a system to execute a chain of actions without a human in the loop verifying the final step.
Which is what AQ is slowly moving toward.
Right. But the second and far more dangerous threshold is recursive self-improvement.
Now wait. If recursive self-improvement means the AI can evaluate its own underlying architecture and rewrite its own code to make itself smarter, how do you even contain that?
It's tough.
Like, if the safety of this digital species relies on engineers deliberately not designing recursive self-improvement, what happens when a bad actor, or honestly just a curious researcher, decides to try it anyway? How do you air-gap an intelligence that operates on global data networks?
And that right there is the alignment problem. It's the defining engineering tension of our era. Now, Suleiman approaches it from a governance perspective mostly, but Jensen Huang looks at it strictly as a systems engineering problem.
Okay, so how does an engineer solve it?
He argues that AI systems must be architected with the same rigorous redundancy as commercial airplane flight computers.
Flight computers.
Yeah, in a modern jet, you don't rely on a single central computer to calculate the pitch and yaw. You have triple redundancy. You have 3 independent computers running the exact same calculations simultaneously.
Oh, so if one computer hallucinates a physical value and disagrees with the other two, it gets outvoted.
Exactly. It's outvoted and ignored.
But how does that mechanical redundancy translate to an AI software architecture?
Well, it means you don't just build one monolithic, super smart AI model that does everything. You build an ecosystem of specialized models. You have an action model that generates the plan and writes the code.
Okay.
But sitting on top of that, you have independent secondary monitor models. And these monitor models don't generate ideas. Their sole computational purpose is to evaluate the output of the action model against a strict, mathematically defined set of safety parameters.
Oh, I see. So if the action model suggests a sequence of API calls that violate the safety protocols, the monitor model intercepts the command.
And it shuts the loop down before it ever reaches the external network.
So it's a built-in automated system of checks and balances.
Yes. But beyond the software architecture, Huang points out there is a hard physical limit to how fast these capabilities can scale anyway. The ultimate ceiling isn't the mathematics of the neural networks, it's the electrical grid.
Oh, right, because flipping billions of transistors and transporting information across a microscopic chip requires immense physical power.
Energy is the hard limit. During his interview, Huang actually held up a prop. It was a physical model of the first AI supercomputer NVIDIA delivered to OpenAI back in 2016.
Okay.
That machine cost $250,000. Today, a modern equivalent performs the exact same calculation 6 times faster, but the staggering metric is the energy efficiency.
How much more efficient is it?
That 2016 computer required 10,000 times more power to perform the same math as the systems they are deploying today.
10,000 times. That level of hardware optimization is difficult to even process. That's the equivalent of a car suddenly getting 10,000 times better gas mileage in under a decade.
The progress really is completely unprecedented.
Yeah.
And despite the profound risks of autonomy and recursive improvement we just talked about, both Huang and Suleiman point to an incredibly optimistic payoff for the individual user, provided we engineer those guardrails successfully.
Right. And when we look at how this actually alters your daily life, the listener's daily life, Huang uses this really fascinating analogy about how a modern GeForce graphics card renders a 4K television display.
Oh, I love this analogy.
It's so good. So a 4K screen has roughly 8 million individual pixels. But the computer isn't wasting computational energy perfectly calculating the light and color of all 8 million pixels. It only does the heavy algorithmic lifting for about 500,000 of them.
Right, and then the GPU uses specialized AI models to predict and fill in the remaining 7.5 million pixels flawlessly based on the context of those core pixels.
Exactly. It saves an immense amount of energy and time while delivering an indistinguishable perfect result. And Huang applies that exact computational analogy to human cognitive energy.
Yeah.
In the near future, these agentic AI loops will take on the vast drudgery of our daily tasks, the scheduling, the preliminary data synthesis, the routine code generation. The AI will basically predict and fill in the 7.5 million mundane pixels of our day.
Which is huge, because that allows you to focus all of your precious human attention and creative energy on your own 500,000 pixels.
The high-value, deeply strategic, empathetic work that a machine just cannot replicate.
It really forces a fundamental shift in what we define as productivity.
I look at this shift the same way we look at the implementation of the interstate highway system.
Amy?
Well, when we laid down those massive concrete highways, the immediate goal was just to speed up travel and logistics, drive from point A to point B faster. But the second-order effects birthed entirely new economies. The highways created the modern suburbs, the logistics networks for fast food, the motel industry.
No, that's a great point.
AI is our new cognitive highway system. We are laying down the neural asphalt right now, and we are barely beginning to understand what the suburbs of the mind are going to look like.
Which makes Huang's ultimate advice to everyone listening incredibly practical. Go get an AI tutor immediately.
We're using it right now.
Exactly. Engage with these models, learn how to construct sophisticated prompts, and understand the limitations of their context windows.
Right.
Because these systems are not being engineered to make human cognition unnecessary.
Right.
They're being engineered to make you superhuman. It is the equivalent of having an incredibly capable, context-aware R2-D2 in your pocket, amplifying your ability to navigate both digital and physical environments.
Which circles us back perfectly to Mustafa Suleiman's breakfast conversation with his nephew. Because when he finally formulated the right answer for that 6-year-old about what an AI actually is, he realized it isn't some alien intelligence that just fell out of the sky.
Right, it isn't a separate entity at all.
It is a distilled reflection of us. I mean, every single piece of digitized art, literature, scientific research, and casual human conversation has been compressed into the weights of these neural networks.
It is our collective empathy, our flaws, our curiosity, and our boundless creativity rolled into an interactive digital species.
So we have traced this evolution from the sequential limits of early processors to the parallel power unleashed by video games. We saw how CD bridged the gap, allowing neural networks to brute force edge cases and scale up by 1 billion times.
1 billion times, just mind-blowing.
And we explored how these models are transitioning from passive oracles into agentic loops with a real-world action quotient, and how they are mastering Newtonian physics inside simulated hyperrealities.
The matrix for robots.
The matrix for robots, exactly. And of course, we examined the critical systems engineering required to keep this new digital species aligned with human intent.
It really is the most complex engineering challenge humanity has ever attempted, but the potential for human augmentation is just staggering.
It really is. But I want to leave you with a final thought to ponder regarding that reflection of humanity. If AI is ultimately a distilled compression of our accumulated knowledge, what happens when these models finish consuming all the high-quality human-generated data on the internet?
Which is coming soon.
Very soon. We are rapidly approaching that physical limit. As these models generate more and more of the text, code, and images we consume daily, will this new digital species eventually have to start training on its own synthetic data? And as that feedback loop tightens, learning from its own AI-generated creations, what will the reflection in the mirror look like then? Will it still be a recognizable reflection of us, or will the feedback loop create something else entirely? Because the processors that used to render the pixelated corridors of our childhood video games, they aren't just tools anymore. They are talking back. And we are the ones who have to decide what they are allowed to become.